2, 1. All right, let's evaluate where we're at. We're halfway through the semester, and now we're beginning the back half of the course, and that means it's time for the real shit. All right, so let's get going. All right, so what's the plan for today? All right, last time we defined what it meant for a function to be continuous at a point. And so given a set and a function defined on that set, we will say that the function is continuous if it's continuous at each one of the points of its domain. So when we refer to a function being continuous, that's what we mean. It's continuous at each point, right? Note the way we define continuity was you are continuous at a point, and here we have continuity defined for a function. A function itself is continuous if it's continuous at each point. All right. So recall the following things that we learned from calculus. The extreme value theorem. Every continuous function attains its minimum and maximum. Our textbook refers to these as absolute minimums and absolute maximums. And there's reason to define them that way later on when we get to derivatives, where we'll be talking about local min and local max. But for us, we'll just say max and min, and it'll be clear what we mean. Okay, more on local max and local min later in the semester when we get to derivatives. By later in the semester, I mean like literally next week? Yeah, like literally next week. All right. Anyway, and the other famous value theorem, one of the 4 value theorems we learn in calculus, the intermediate value theorem, given a continuous function, and a output that lives between two of its a real number lives between two of its outputs, then there is a real number, so that that intermediate value is attained. Yay! All right, so obviously, the goal of this course is to prove everything that we learned from calculus. So our goal is to prove these 2 theorems. That is what we will do today. In fact, we are going to do a little bit better. And so here's another case of us going a little bit off book. We're going to approach both of these theorems slightly differently than how our textbook does it. Although the proofs are going to be essentially identical, but the formatting is going to be a little different. Okay. So as we learned in calculus, the closed interval AB is very important for a variety of functions. So specifically for the extreme and the intermediate value theorem, as we hopefully remember, if you start screwing around with the domain, you can't necessarily guarantee that these theorems hold. All right. And later on, of course, we talk about the mean value theorem and the average value theorem. Again, the same is true. We need the intervals to be closed and bounded. There are continuous functions on different domains that don't exactly behave well. But, of course, like everything that you were taught in calculus, you were horribly lied to, because while it turns out that a closed bounded interval AB and a closed bounded interval AB work, there are actually much more general sets that these theorems apply to, and that's going to be part of the story today. So we will be proving these theorems, but we will also be going as general as we can given the machinery we have. It's not the full-out general version of these theorems, but the most reasonable general one we can expect to prove. So if you are interested, there are much more general theorems related to these 2. I'll talk about them as we go a bit further. And after we prove the 2 theorems, our goal is to, we'll finish things up by demonstrating some fundamental theorems regarding our good friend the polynomials. Okay. Plan the work, let's work the plan. Okay, so first things first, we're going to rehash something that we've kind of already talked about. So, given a subset of the real line and a function, we say that our function is bounded above if its range is a bounded above subset of the real line. Likewise, the function is called bounded below if its range is bounded below, and we'll call it bounded if its range is bounded above and bounded below. And the following is true, and its proof is identical. There you go. I never said I had a PhD in spelling. Anyway, but and the proof is identical to the one we did for sequences, because these definitions should look familiar. These are precisely the definitions we did for a sequence to be bounded above, bounded below, and bounded. And recall, a sequence is simply a function. So that's that. All right. So indeed, a function is bounded precisely when the absolute value is always less than or equal to some real number b. And as we've previously noted, the theorem doesn't require us to know anything about b, but in practice you can always make b be strictly positive. You can make b be an integer, by a natural number, by the way, if you are so inclined. But yeah, all right, cool. So there we go. All right, so let's now introduce something that is not in our textbook, but is something that, if you look in other real analysis books, they'll talk about them. It's a really neat property, which is the following. So a subset of the real line is said to be closed if, given any sequence that is convergent, contained within the closed set, the limit does not escape the set. Ah. Hey, our good friend, a closed bounded interval, AB, is in fact closed. Beautiful. And this is super easy to see, because if you have a convergent sequence, well, all of the elements are bounded below by A and bounded above by B, so we know that the limit of the sequence has to stay within there, and thus the limit is in the set. So there we go. Cool. Now, it turns out, with the extreme value theorem and the intermediate value theorem, the proofs that are in our book, right, are done using sets that look like this. It turns out, though, you don't really need your sets to be this. What you really need is this property right here. So we are going to do the proofs with this condition. Now, it's not too difficult to show that if you that there are other closed subsets of the real line. In fact, there can be some very bizarre closed subsets of the real line. So the theorems we're about to prove will be focused on closed subsets, so sets with the property that a convergent sequence's limit does not escape the set. Right, so as was traditionally done initially in the history analysis, everyone just looked at closed intervals AB, but then, of course, throughout the 1800s, as people started digging through and getting a little bit more precise, a couple of mathematicians noticed that really what they needed is this property, and it's pretty easy to cook up sets that are not closed intervals that have this. So, for example, a union of two closed intervals will actually have this property. Which is not the worst proof ever, because it's pretty easy to see, because the limit, so for example, if you have two closed intervals unioning up, a sequence that converges, the limit has to be in one of those sets. A little exercise if you want. But anyway, so like I said, we're going to go a little off book from how Lebel does things. So, for example, Lebel proves the following, where K, of course, is the interval AB. But we're going to do it for any closed set and any bounded set. And the reason I decided to do this is because, as you'll see in the proof, the boundedness of the set and the fact that limits don't escape the set are the only two things in the proof that are used. And obviously the continuity. Yeah, so this is literally exactly the same proof that is in Lebel, but we're just doing it with a different style of domain. And this is giving you a little sample of a branch of math called topology, where you investigate things called closed sets. You also talk about things called open sets. And it just so turns out that closed and bounded in the real line is equivalent to a property called compact. And I'll talk a little bit more about that in the next video, actually. A little math deep lore. But anyway, okay, so like I said, Lebel does this for the interval, closed interval AB. We're going to do it for closed and bounded, because, as we'll see in the proof, that's all you need. You just need limits don't escape, and we need the set to be bounded. And that's it. Okay, so let's do the proof here. Suppose f is not bounded. All right, well, if it's not bounded, that means for every natural number, I can find an element in K so that the absolute value exceeds K, right? If it was bounded, then there would be an N that all of them are less than. Okay. Now, our sequence here lives in the set K, and the set K is bounded, which means my sequence must be bounded, so Bolzano-Weierstrass guarantees a convergent subsequence, and this maneuver right here of passing things through a convergent subsequence is going to be our bread and butter this week. This is the key maneuver. So good thing we spent like an entire week talking about how sequences work, and in particular proving the Bolzano-Weierstrass theorem. Okay, so we have a subsequence now. It must live in K because it's, right, effectively a subset of this. And note that it has a limit, and by the assumption of closed, the limit does not escape the set. So what do I have now? I have a sequence that lives in my set K. It converges, and the thing it converges to is in my set K. And hey, I've got a continuous function, and continuous functions like limits. Specifically, the continuity f guarantees that this sequence then must converge to f of x, but as you hopefully can already see, oof I'm a goof, that's not going to work, right? Because a sequence being convergent means that the sequence is bounded. So that means this has to be bounded above by some b, but we can find a capital N that's strictly bigger than b, and thus capital N, which is less than or equal n sub n, so remember a subsequence, this is a strictly increasing function of k, so that means n must always be less than or equal to n sub capital N, and by the construction of the elements x sub n, we know this must be true. Right, but this is convergent, so it's bounded, so we got it less than a b. Then we chose n to be strictly bigger than it, and we get our favorite contradiction. N is strictly less than itself, so it's got to be that our function was, in fact, bounded to begin with. If it failed to be bounded, then it would have failed to be continuous, but we assumed continuity. So there we go. Beautiful. So, like I said, this is precisely the proof that appears in our book, but right, the domain that they use is a closed-bounded interval A to B, right, so they use the boundedness to apply the Bolzano-Weierstrass theorem, and then they use the fact that a limit of a sequence living in an interval A to B is not going to escape it. So there we go. Beautiful. Alright. We now have all of the tools we need to prove the extreme value theorem. And like I said, we are going to prove the most general version of the extreme value theorem that we are capable of proving. So take any non-empty, closed, and bounded subset of the real line, and take any function that is continuous. Then the function attains its minimum, and the function attains its maximum. Okay. And again, our textbook refers to these as the absolute minimum and the absolute maximum. Local minimum and local maximum, of course, these are things we hopefully remember from calculus. We will discuss those next week. All right, but for now, here's what we'll prove. So there is a f of x that is the smallest. So f of x is less than or equal to f of t for all t. And likewise, f of y is the biggest. F of t is less than or equal to f of y for all t. Okay, so this is the extreme value theorem. Okay. All right, and so again, our textbook proves this where k is the interval AB, but we are going a little bit more extreme now, aren't we? Okay, so let's do the proof. Okay, so the proof is super easy because we basically already did the hard part. Because my function is continuous, the previous proposition guarantees that it's bounded, which means that this set right here is non-empty by our assumption, and bounded above and bounded below. That's what it means for a function to be bounded. So it's got an inf and it's got a sup. The only thing I need to do now is verify that there is an input that equals alpha, and there is an input that equals, and there is an output that equals beta. That would guarantee that our infimum is in our set, so it must be our minimum. Likewise, the supreme's in our set, so it must be our maximum. Okay. And we're going to be lazy. We're going to be very lazy today, actually. I'm going to prove the former and note that a similar argument gets you the latter. So we'll demonstrate the existence of x, so that f of x is equal to alpha, and you can modify it to show that there's a y that hits the supremum. Okay, beautiful. All right, so let's do it. Okay. Now, alpha is the infimum of the range of our function. Okay, so if I make it a little bit bigger, it's no longer a lower bound. Right, this is strictly bigger than alpha, and alpha is the biggest possible lower bound, so this cannot be a lower bound, so I can find things that are less than it. Right, otherwise, right, it would be a lower bound. Okay, so for each n, I can find an x sub n living in my set K. Again, my set K is non-empty, closed, and bounded. All right, now by the construction of my x sub n here, oh god, why do the alphas turn the betas all of a sudden? The alpha's the infimum. Oh my god. Oh my god. I gotta fix that. Yeesh. That one's annoying. That's alright, anyway. Alright, cool. Alright. Okay, so again, alpha is the infimum, so if I make it a little bit bigger, I can find things that are less than it, because this fails to be a lower bound. Okay, now alpha is a lower bound, so alpha is always less than or equal to f of x sub n. So that means the following must be true. So we've pulled this maneuver before. All right, so that gives me this right here, and we know that that guarantees that my sequence there then must be converging to alpha. Okay. Now, we're not quite done. All right, it seems like we're done, but we're not, because I proved the outputs here are converging. I don't know anything about my inputs, right? There's nothing here that tells me that x sub n actually converges to something. But, good thing that my sequence lives in a bounded set, so by Bolzano-Weierstrass I can find a convergent subsequence, and the limit it converges to, because my set is closed, does not escape my set. So there is a subsequence of these things that must be convergent, and the limit must live within our set. So again, that's using the boundedness and the closed osity of my set. And now, by continuity, we're done. Because the limit, as k goes to infinity, of these must equal f of x. That's the continuity coming in. This is convergent, so any subsequence must converge to the same thing, as we proved. And this was constructed so that it converged to alpha. And there we go, there is an x, so that f of x is equal to alpha. And there we go. That was what we wanted to show, and that completes the proof. So you could do the same thing for the supremum, only difference is instead of adding 1 over n, you subtract 1 over n, and then the argument is virtually identical. But you are free to fill in the details. Okay, alright, so there we go. The extreme value theorem proven. So the first of our 4 value theorems has now been demonstrated. Hooray. Okay. Alright, so that's 1 down, 1 to go. Alright, so our next task is to verify the intermediate value theorem. And before we do that, let's introduce the set we're going to perform it on. Okay. So, as I noted in the first slide, the subsets that we typically state these theorems on in calculus are closed-bounded intervals AB. But it turns out there's more general sets that they hold on. So for the extreme value theorem, it turns out that what you want is closed and bounded. For the intermediate value theorem, it turns out what you want is what we call a interval. So yeah, when we say an interval of the real line, we mean a set with the following property. Given any 2 elements x and y that live in I, then the open interval from x to y is contained in I. Or, equivalently, you can include the endpoints if you want. obviously. All right, no, so obviously when we say interval, and we think about subsets of the real line, we immediately think of stuff like, the closed intervals, the open intervals, the half-open intervals, open rays. Well, it turns out that all of them satisfy this definition. So, in fact, the only subsets of the real line that have this property are truly intervals, in the sense that they must be of the 8 forms that we usually think of, and also the real line. Right, the real line is an interval, if you think about it. It's just arbitrary, right? It's an interval. It's a huge one, right? It's negative infinity to negative infinity. All right, yeah. So this is the technical definition for what an interval is. It's right. You could define an interval to be, any set that looks like these things, but it's not quite right. It turns out that an interval is anything with the following property. So these are actually sometimes called formal intervals, because, shocker, in weirdo ordered sets, there are intervals that are not necessarily of these forms. Because, but for the real line, they line up, so we like them. Alright, so similar to the extreme value theorem, where we prove that for closed bounded sets, we're going to prove the EME value theorem for intervals. Alright. So before we do that, though, we'll first prove that intervals are precisely what you think they should be. They're either the real line, and that only happens when we're not bounded above and not bounded below. They are rays, open or closed, if you're bounded below and not bounded above, or vice versa, bounded above and not bounded below. And if your interval is bounded above and below, then it's one of the following sets. And again, note what the A's and the B's are. They're infimums and supremums. Right? Since it's a non-empty set, if it's bounded below, we know it has an inf. And as we've already just demonstrated, right, this set has an infimum, but it doesn't belong to the set. This one has an infimum, but it is in the set. So the two possibilities there are hopefully clear. Right, so why there are two possibilities. So you may or may not contain your infimum, so you contain it, you don't contain it, or you do, and vice versa. And here you've got two things, so there are 4 possibilities of containment. All right, so let's do the proof here, and the proof of this is actually pretty easy, if not like tedious. Okay, so first things first, we'll prove that if we have an interval that is not bounded above and not bounded below, it's got to be all of the real numbers. Okay, so take any real number. Since I is not bounded below, there's something in the set that is less than it, right? Otherwise, it would be bounded below by R. Likewise, since it's not bounded above, there's something bigger than it. And hey, X and Y both live in I, and so since it's an interval, the open interval is contained inside of it. And hey, look, R lives in there, so hey, that means the real line is a subset of I, and since I is a subset of the real line, they must be equal. Beautiful. Alright, similarly, so for point 2, we have that I is bounded below, right, and A is the infimum. Now, take an element that lives in this set. I is not bounded above, so there's something bigger than it. Moreover, A is the infimum and R is bigger than it, which means that R cannot be a lower bound, so I can find something out of my set that lives between the two. And there we go, same argument from before. I have that R is in this set, and this set is contained in I by hypothesis. So this means that the open ray is contained in I. Now, note, I is contained in here because anything that's in I is less than A, because A is the infimum, meaning that it's a lower bound. But now we just demonstrated that this set is contained in I. The difference between this set and this set is just the element A. So I, if it does not contain A, must equal this set. And if I does contain A, it must equal that set. So it's got to be that I is one of them. Pretty neat. That's a cool little proof. I like that proof. And point 3, which is the case of I is bounded above but not bounded below, it's the same argument, only the imps are soups and the orderings are reversed. So if you feel like writing out the details, be my guest. Okay, so let's wrap it up. So let's say you have an interval that's bounded above and below, then it's got to be either our usual closed interval AB, open interval AB, or one of the half open intervals from A to B. All right, and then we just follow the exact argument from above. Take an element R that lives between A and B strictly. Okay, well, this is the infimum, that is the supremum. So if we're bigger than the infimum, I can find something less than it that lives in the set. And if this is the supremum, R is less than it, so that means R cannot be an upper bound, so I can find something bigger than it. All right, and thus R lives in that, so that means that the open interval AB is contained in I is contained in the closed interval. The only difference between these two sets is the elements A and B, so either both elements are in I, both elements miss I, or one of them is in there and the other one isn't. And there we go. Cool. So now, whenever you say interval of the real line, what you mean is a set with the property that given two elements in I, then the open interval is contained in I, and this now subsumes all of the usual intervals that we normally deal with. So the closed intervals, the open intervals, the half open intervals, the open rays, and the closed rays, and in fact the real line itself. All right, and now with this new type of set established, we can formally state the most general version of the intermediate value theorem that we are currently capable of proving, which is given any interval and a function that is continuous on the interval, take a real number that lives between f of a and f of b, where a and b are elements n of I, then there must be a element c in I, so that f of c is equal to y. So intermediate values are obtained. Beautiful. All right, so that is the most general version of the intermediate value theorem that we can prove. And in fact, it's a much better version than the usually stated one, where the set I here is the closed interval AB, because, as we just verified, the real numbers themselves are an interval. So any function that's continuous from the reals to the reals obtains intermediate values. So I think this is a much better way of handling it. I mean, we did have to spend a minute talking about these things, but it's going to give us a much more versatile theorem, and it's a much more general version of the theorem, and it's more in line with the most general version of the theorem. That, of course, as I've kind of already hinted at, lives in the world of topology, where I is something called a connected set. It turns out that the only connected sets of the real line are intervals, so, like I said, most general that we can currently prove. Yeah, but if you're interested in topological things, we can talk about it. Alright, so let's do the proof of this. So, it's worth noting that our proof is going to be different than Lebel's. Lebel's goes for like an algorithmic proof. So he basically proves that something called the bisection method converges, which is nice, but I don't know about you, I like least upper bounds, so I'm going to do it that way. Okay. Alright, so the first thing to note from our hypothesis is that A and B cannot be equal. Right? F of A is not equal to F of B, so A and B have to be different things. So either A is less than B or B is less than A, and we'll do the case that A is less than B. If B is less than A, you just relabel them. Oh god, Olive attack. My cat just showed up. She was actually here earlier, but she left, but now she's back. Okay. So, yeah, there we go. Okay. So, now we define the set E as follows. E is the set of things that live in A to B, so that f of x is less than y. Okay. By hypothesis, A must be in our set, so E is a non-empty bounded above subset of the real line. So it's got a supremum. Furthermore, the supremum has to live in the interval AB. right? Because E is a subset of AB, and its sup has to be in that set. The sup is definitely bigger than A, and B is an upper bound for the set, so the sup is got to be less than or equal to it. So it lives there, and since I is an interval, we know that this closed bounded interval must be contained in I. Alright, so by the trichotomy property, f of c, where c is the supremum of the set E, is either strictly less than y, equal to y, or strictly bigger. And again, we are going to be lazy. I'll show you that this can't work, and then I'll say this has an incredibly similar proof, just fill in the details, which then forces the equality, which gives us the result we're looking for. All right, so it's worth noting that the interval part of this is the only spot where it actually shows up. Everything else from this point forward is literally just going to be the continuity of the function. So note, right, we could have really have done it if it was AB, but it's worth noting you can generalize it to an interval, and it's more applicable, and it's more in line with the most general version of the theorem. So, all right. Okay, so let's verify that f of c cannot exceed y. Okay, so suppose that was true. Now, note that f of b is bigger than y, so c and b have to be different. And c lives in the interval ab, so c is less than b. So that means c is strictly less than b. Right now, that seems like something completely pointless. But note that b minus c is strictly positive. Yeah, I wonder if we're going to use that. Okay, now let's let epsilon be y minus f of c divided by 2. We're doing this for reasons, because, hey, note, this is strictly positive. Hey, I have an epsilon and I have a continuous function, so the continuity gives me a delta, so that f of x minus f of c, an absolute value, is less than epsilon for all x that live in my interval I that are within delta of c. Now I'm going to let eta be the minimum of delta and the minimum of b minus c, and as I noted, b minus c is strictly positive. Now you might be looking at this and going, okay, why the hell are you doing this? You also should have been saying that right here, where why are you doing that, other than, well, I have continuity, so I need an epsilon to get a delta, and then I'm doing this for reasons. Let me tell you why I'm doing that. Alright, eta is positive, so c is strictly less than c plus eta. Okay. So that means I can find you a real number that lives between the two, or pick a rational or pick an irrational. Pick any real number. I don't give a shit. Alright, now why am I picking this? So why am I doing this? Okay, so the first thing to note is that a is less than or equal to c, because again, c lives in the interval ab. Okay, x is chosen to be strictly less than it. C plus eta is bigger than it. Eta, note, is less than or equal to b minus c, and oh hey, look at that. My number x here lives in my closed bounded, lives in my interval ab. Moreover, x minus c, an absolute value, as chosen, has to be less than or strictly less than eta, and eta is less than or equal to delta. Oh, hey, look, x minus c is less than delta. Yeah, I guess it's less than epsilon up there. Okay, so the first fact guarantees that x lives in the interval ab, which means it lives in our interval I. Moreover, x can't actually be in the set E. C is the supremum of E. If x is bigger than it, x doesn't live in E. And remember how E was defined. E is the set of x, so that f of x is strictly less than y. So that means y is less than or equal to f of x. Alright, but x minus c is less than delta, so the continuity then guarantees that this is less than epsilon. But then we get the following favorite contradiction. Epsilon, note, it was always less than 2 epsilon. 1 is less than 2, and epsilon is strictly positive, so multiply it across. 2 epsilon, as chosen, is y minus f of c. Y, as we just noted, is less than or equal to f of x, and f of x minus f of c is less than epsilon, and hey, epsilon strictly less than itself. Oof, I'm a goof. Beautiful. Alright, so yeah, lots to digest right there. So this is a technical beauty right here. This is a proof that's got details, very subtle. Bravo, Nolan. This is this is a proof, right? Um, I personally, I love it. I'm a big fan of this proof. I just the technical messiness of this proof is just so, it's gorgeous to me. Whenever you have like Adas showing up to the party, that's when you know you've gone up the deep end. But yeah. So note, lot to unpack, a lot going on here, and this is definitely a good example of a proof that, right, the way I worked this out was not how I presented it. Right, I figured, right, right, when I first learned this proof, it was given to me like this, and I was like, okay, some shit's happening. And then when I went to create it on my own, I had to dig through it and go, all right, I got to use the continuity, so that's why I need some epsilon. The epsilon gives me some delta, but the delta on its own is not good enough because I don't know, C is strictly less than C plus delta, but that doesn't guarantee that what I pick between there actually lives in the interval AB. So that's why I got to do this nonsense. Now, the positive epsilon, right, is going to guarantee this, and the contradiction here that we're picking up in the end, you're right, you're only going to piece that together by noting that, well, picking x to be bigger than c guarantees it's not an e, which means that f of x is bigger than y. And then you kind of look at this, and then you go, well, that's less than epsilon, so choose epsilon, so that on the left we get hosed. So, a lot of detail, a lot of ins, a lot of outs, a lot of what have yous. This is a very dense slide right here, why I'm taking time to keep talking about it. But yeah, like I said, it's this is technical, and it's great. I love it. Hopefully you enjoyed it. If not, well, I had fun. All right. Speaking of technical garbage, as promised, we are going to prove the intermediate value theorem and the extreme value theorem. We have now done that. The other thing we're going to do is show how these very important theorems tell us very important things about polynomials. Facts about polynomials that you know but do not know how to prove. Okay. So, before we get there, let's prove something else that is also a little bit technical. So let's take a natural number n, a list of real numbers starting at 0, for reasons. And let's let n be the maximum of that stuff, because why not? And then take x to be a real number who is bigger than m in absolute value. Then 1/2 is always less than or equal to this. Yeah, sure. Right, at first glance, as per usual with this sort of stuff, this especially today, is going to be one of those like, yeah, all right, yeah, I bet this is a thing. The proof of this is actually not too bad, and the power of this particular proposition is astounding, as you will see. Okay, but right at first glance, this just looks like this is like an analyst's wet dream. Look at all this. Look at all this maximums and inequality. Oh boy. All right, so let's do the proof of this. Okay, so the first thing to note is that we snuck a 1 in here, and right, that's really just to kind of make this work like this. So 0 is strictly bigger than strictly less than 1, and m is strictly less than x. So for any k living between 1 and n, so note. Then, if I look at 2n, a sub n minus k, all right, well, that's one of these things on the list. That's less than or equal to m. M is less than that. And now, since x is strictly bigger than 1, when you start taking powers of it, it's going to get bigger. And as we proved about absolute values, you can pull in the absolute value as thus. All right, now x is strictly bigger than 0 in absolute value, so I can cross multiply both sides now and end up with this strict inequality. Oh, a 1 over 2 to the n, and oh hey, do I have n of these? Oh, I do, don't I? Alright, so now, if we look at this in absolute value, triangle inequality gets me that. Each one of these, as I just demonstrated, is less than or equal to 1 over 2 to the n, strictly. And n of these show up, so this is strictly less than 1/2 in absolute value, which means that it's bigger than negative 1/2 in absolute value, and then we add 1 to both sides. You know, for funsies. I mean, there's a reason we do that, as you will see, but there we go. Alright, so now that we're equipped with this, we can state and prove a fundamental theorem. A very important fundamental theorem, the one of algebra. Alright, so what is the fundamental theorem of algebra? So, if you've ever heard that phrase, you've probably heard it in the context of the following: every complex polynomial has a complex root. While that's true, that's not really what you actually end up proving, depending on how you approach the proof. If you've taken 365 complex variables, you know that you actually prove it using Liouville's theorem. But there is another approach, and in fact, historically, this was the approach that mathematicians took. So it turns out that for any odd degree real polynomial, it always has a root. And this is really the fundamental theorem of algebra. The fact that every complex polynomial has a complex root, in some sense, is just a generalization of this. And this theorem right here is really the hard part. And that actually is a stance that mathematicians were pretty hard on for a pretty long time. So this theorem, as stated, this was originally proven by Euler. Our boy Euler is the one who verified that this is true. Doing a proof that basically we are about to do. As far as I know, this is like exactly what he did. Now, the complex variable version of it was actually proven by Gauss for his PhD thesis when he was 21. So, you know, if you want to compare yourself to Gauss. But Gauss caught shit. Because everyone said what he actually proved really wasn't anything worth noteworthy, because as people pointed out, Euler really did the hard work. The hard work is this, because once you have this, the complex variable one is kind of just, you just fill in the details to get it to work. Although there are proofs that don't use this now, as I've already noted, you can do it using something called Liouville's theorem if you got some complex variable theory. But anyway, so our fundamental theorem of algebra is that every odd degree polynomial has a root. Note here, we are assuming the leading coefficient is 1. You can have the leading coefficient be any non-zero real number, and this theorem is still true. It's just a hell of a lot easier to prove when the leading coefficient is 1. So that's what we're going to do. Alright. Well, there we go. Alright, so the fundamental theorem of algebra. Proving it in analysis. That is actually also another joke about the name of this theorem, is that there is no proof that only uses algebra. Now, somebody recently published a paper claiming that they've got a proof that uses only algebraic techniques, but they use something called the hyperreal numbers, and as far as I'm concerned, that's not algebraic, so I don't believe them. But if you're interested, you can go look it up. It was 2016. 2018. I forgot who proved it. But anyway. Alright, so let's do this proof. Now, the good news is that this is literally just the intermediate value theorem. And we're going to use our little technical lemma that we set up. So let m be the maximum of that junk right there. Alright, now we can find a positive real number so that m is less than r and less than negative r. So you can find such an r pretty easily. We know that there are natural numbers bigger than m. There are natural numbers that are bigger than negative m. So just take the big maximum of the two things. Whatever, we can find an r that does this. Note that guarantees that the absolute value of m is less than r, and r is non-negative, so it's equal to its absolute value. So as we proved, we must have this. Now, r to the n must be positive, so if I multiply it across my inequality here, I get 0 is strictly bigger than this. And hey, when you multiply this by r to the n, you get our function. Hey! There is somewhere where f of r is bigger than 0. If I could find somewhere where f of some input was negative, that would mean that by intermediate value theorem it was equal to 0 somewhere. Oh, hey, r is equal to the absolute value of its negative, so that has to be true. And since we're odd, negative r to the n is equal to negative r to the n, which must be negative, because r to the n is positive. Multiplied across, swaps the inequality, and there we go, f of negative r is negative. By intermediate value theorem, there's a c, so we're done. Beautiful. There we go. There we go. So every odd degree polynomial must have a real root. So first order polynomials, which are just lines, third order cubics, fifth order quintics, so on and so forth. Hooray! And in fact, this actually tells us that every odd order polynomial is actually surjective. Which, if you think about the graph of an odd order polynomial, you already knew that to be true, right? Draw a graph of x cubed, draw a graph of x to the fifth, draw a graph of x to the seventh, right? It obtains every real number. Okay. So, let's prove it. So, define our function g to be basically f, but instead of a naught, it's a naught minus y. Fundamental theorem of algebra says that's equal to 0 somewhere. That means this is equal to 0, and then we just add y over, and then we get f of c is equal to y. So f is surjective. Beautiful. There we go. Good stuff. Cool. So again, like I said, facts that you knew about polynomials coming into this video today, but now you got proofs. Now you got excellent proofs of them. So, every odd degree polynomial is indeed surjective. Very cool. Alright, well, if that's the truth for odd degree polynomials, what can we say about even degree polynomials? Alright. Now, obviously, the fundamental theorem of algebra does not apply for even degree polynomials. X squared plus 1 is never equal to 0. X squared plus 1 is obviously not surjective. But x squared plus 1 has an absolute minimum, and every value bigger than the minimum is obtained. That's going to be what we're going to prove. So it turns out that for odd degree polynomials, the story is beautiful. Every odd degree polynomial is surjective. It has roots. The end. The evens, on the other hand, not necessarily true that they're surjective, but there is an interval where it obtains all of those values. And in order to prove that, we once again need to prove a technical result, which is the following. So take an even natural number, take a list of real numbers, and take a real number y. Then there is a positive b, so that every x bigger than b in absolute value, the output of my polynomial exceeds y. So, in other words, this is saying that if we have an even polynomial, there is some point where the output of the polynomial is always bigger than y. And it's symmetric, right? So for all values, so that b is less than x in absolute value, so all x strictly bigger than b, and all x strictly less than negative b. And if you think about what x squared looks like, and if you think about what x to the fourth looks like, and when you think about x to the sixth looks like, you can pretty easily convince yourself this is true. But let's do the proof. And now this one, if you thought some of the proofs we've done today are technical, this one, this is a beauty. I love this one too. This is another scoop-de-whoop one, I guess. I don't know. All right, so let's let m once again equal the maximum of all that junk. All right, so just keep that in mind for a moment. Now, I have to be able to find a real number that's strictly bigger than this. Okay. This is just some real number on the left, so there's some are bigger than it. Give me a natural number, whatever you want to pick. Let b be the maximum of r and m. All right, and the reasoning for being bigger than both of these will become apparent as we go forward. Okay, so first thing to note, obviously, m, of course, we sneak the 1 in, so we know that m's bigger than 1. All right, so that means that b is, first of all, positive, and also bigger than 1. Now, 2y minus 1 over n plus 1 is... I'm missing a plus 1 there. There we go. Let's get that in there. There we go. There was supposed to be a plus 1 there. Again, this is just some real number, so there's an r bigger than it. All right, r is less than or equal to b. So I could subtract the 1 over, I can then multiply by n, and then I can add 1 over, and I have 2y is less than this. And, right, at first glance, you might just be looking at this and going, yeah, okay. But hopefully, you noticed it. Your brain certainly did. Because your brain went, aha, Bernoulli, that's right. Note, b minus 1 is bigger than negative 1, so Bernoulli's inequality guarantees that 1 plus n times b minus 1 is less than or equal to 1 plus this to the n, but hey, that's just b. Ooh, hey, there's an inequality that we proved coming back. Beautiful. All right, so here you have 2 to the y is less than b to the n. Okay. All right, well, hopefully you can see why we set this up here. That guaranteed all this came out good, and we got our b to the n. All right, but what's with them? Why is that showing up? Well, remember, m's got a very nice property. Whenever you're strictly bigger than m, we have a neat little 1/2 inequality. So specifically, let's take x down to be bigger than b in absolute value. M is less than b, so that means m is strictly less than the absolute value of x. And then applying that proposition from before, we know that this is true. Now, n is even. X is got to be bigger than 0. So, x has to be non-zero, so x to the n can't be equal to 0. And since n is even, we know that x to the n must be positive. Anything to an even power is positive. So I can multiply both sides by x to the n. And now b to the n has to be less than x to the n, and b to the n was chosen so that b to the n was bigger than 2y, which means that y is less than or equal to b to the n over 2. This is strictly less than that, which is less than this, which is what I wanted to prove. That there exists a positive number b, so that for all x whose absolute value is bigger than b, y is less than or equal to that. Okay, now equipped with this highly technical result, we now make our first step towards proving not that every even-ordered polynomial is surjective, but every even-ordered polynomial is as surjective as it's going to be. So specifically, we will now prove that every even polynomial has an absolute minimum. And again, we're doing it where the leading coefficient is 1. If the leading coefficient is positive, this is still true. If the leading coefficient is negative, it's not a minimum, it's actually a maximum that you obtain. So there is a mild difference here with the even ones, and we'll do it where the leading coefficient is 1, but every even polynomial has a minimum. Beautiful. Right, and again, note, all real numbers. So again, think of x squared. There is an absolute minimum to it. X to the 4th, there is an absolute minimum. Something like x to the 4th plus x squared plus 1. That makes like a nice little w. There is an absolute minimum. All right. So that is going to be our goal, is to prove this. So how are we going to do it? Well, good thing we have a theorem about minimums existing. So first things first, the previous proposition guarantees a positive b, so that for every x whose absolute value is bigger than b strictly, there is, we always exceed y. Now remember, in the previous proposition, y was arbitrary, so you can pick y to be whatever you want. So we'll pick y to be f of 0. Okay. Now note, f of 0 is actually a naught, so if you wanted to write a naught, you can, but f of 0 is better in this case. Okay, so that's true. Now, why do we need that? Well, now I have a b. I can make my closed interval negative b to b. Now note, this is closed and bounded, so the extreme value theorem applies. So the function g, which is just the function f, but restricted to this must have a minimum by the extreme value theorem. Note that 0 lives in that set, so g of c is less than or equal to g of 0. Okay, so what have we done now? So we have found a c, and it's related to my f, right, but we got it from restricting f to the interval negative b to b. All right, well, good thing I have this. So I claim that f of c is less than or equal to f of x for all x, and that yields the desired result, and I claim we've already got all the material for this. So let x be a real number. If x is less than b in absolute value, that means x lives in the interval negative b to b. F of c is equal to g of c, because again, g was just f, but restricted to the domain negative b to b. G of c is constructed so that it's always less than or equal to g of x. The extreme value theorem guaranteed this. And here we've got f of c is less than or equal to f of x. And I should have had a pause there, but I did not. So that takes care of the case if x is less than or equal to b in absolute value. Now let's say x is strictly bigger than b in absolute value. F of c is equal to g of c, and as we noted, g of c is less than or equal to g of 0, which is less than or equal to f of 0, but remember how b was constructed. Anything bigger than it exceeds f of 0, but we know that's less than or equal to f of c, and there we go. Every even polynomial has a minimum. All right, and to finish things off for today, we will now verify that every even polynomial has a minimum, and anything bigger than that minimum is obtained. So every odd polynomial is surjective. Every even polynomial is as surjective as it could possibly be. So for every even polynomial, there is a minimum, and anything bigger than the minimum, we obtain those values. All right, so let's finish things off, and good news is we've basically done all of the details of the proof for this. We just got to put everything together. All right, so let alpha be the minimum, which by the previous proposition we know exists. And furthermore, we know there is a so that alpha is obtained. Okay, now if y is actually equal to the minimum, then we just choose c is equal to a, so we can go ahead and assume that y is not equal to alpha. So in other words, f of a is less than y. Now, as we know, we can find a positive number so that for every x bigger than it, y is strictly less than this right here. choose B to be beta plus 1. That is certainly satisfies beta is strictly less than B. That means y then is strictly less than this, and that has to be equal to f of b. So, hey, f is continuous. F of a is less than y. F of b bigger than y. By the intermediate value theorem, we must obtain that value. And there we go. So, we have proven the intermediate and the extreme value theorems, two fundamental facts about continuous functions. Immanuel Kant. He knows about these functions. Anyway, two fundamental facts about continuous functions, and we apply those two fundamental facts to a very important class of continuous functions, the polynomials. Specifically, we prove the fundamental theorem of algebra, that every odd polynomial has a root. Equipped with that, we then verify, in fact, even better, every odd polynomial is surjective. And not to let the even polynomials feel left out, we prove that every even polynomial has a minimum, and anything bigger than the minimum is obtained by the function. So even polynomials are not surjective onto the reals, but they're as good as you can possibly make them. All right. Given, of course, the limitation of the reals, if things were complex, the story would be different. But you should take Math 365 to find out more about that. All right. With that, I'll see you next time. Where we're gonna put our uniforms on.